Okay, everybody are seeing my slides?
Yes, it's okay. Yes.
Thanks, Farid, for your words. And I'd like to thank the organizers for this opportunity, the organizers for the colloquium, and in particular, I'd like to thank the organizer of this thematic section for inviting me. In this work, this is a joint work with Maria Aparecida Ruas, and our purpose in this work is to study, find, determine map-germs from CN to CP for a special class in which P is greater than or equal to 2n. Well, for this, in this work, we define an operation called join operation, and with our purpose is to produce new finely determined map-germs. And with this notion of join operation, we give a general form of a finely determined monomial map-germ in this class. And this is our purpose to show, and we start with some notations. We study map-germs with respect to the A equivalence. A is the classical group, the product of the group R and L, where R is the group of diffeomorphisms from Cn to Cn, and L is the group of diffeomorphisms from Cp to Cp. And we define these two map-germs, F and G, are A equivalent if this diagram commutes or F and G satisfy this relation. It's the classical equivalence relation, and we study map-germs with the property that F is G finite determined, or simply G finite. Here we are interested in the group A and L, and we say that F is G finite if there exists K, so that for any map-germ G with the same K jet of F, implies that F is A equivalent to G, where K jet is the only we truncate the Taylor series in the order K without the constant T. So it's a classical, it's very important class of maps, finely determined maps, studied by many authors. And here, when P is greater than 2n, this result of Gaffney is very interesting because they relate that a map is A finite if and only if F is L finite. So we can restrict to the study to find the term maps to restrict to a subgroup of the group A. It's very interesting. And in terms of invariance in singularity theory, we can, if we denote On, the local ring of function germs in Cn at the origin, and N for us denote the maximal ideal to the local ring On, and ONP is the set of smooth map germs from Cn to Cp, and it's well known that ONP is a free On model of rank P. So in terms of invariance, the infinitesimal criterion of finite determinacy, F is A finite if and only if the A equidimension of F is finite. The equidimension is the complex dimension of this complex vector space. The AEF denotes the extended tangent space to a orbital of F, where we define here in matricial terms, all the elements of the tangent space is defined as all element that we can be writing as an element that is a product of the Jacobian matrix for an element of On, each each element of this, in each line of this matrix, we have an element of ON plus elements that can be written as a composition of an element of the local ring OP with F. So look that this part, the elements of this matrix are exactly belongs to the tangent space, extended tangent space to the L group. And it is easy to see that in each line we have an element in F star OP. F star OP are the set of elements that the composition F star H means 8 composed with F. So here L equal dimension, if we denote delta of F as the dimension of ON over F star OP, it's easy to see that the L equal dimension is P copies of the delta of F. So we can rewrite this relation, this result of Gaffney, saying that F is a finite if and only if delta of F is finite. It's a good result because the computation of the equal dimension in general is very difficult. So delta of F simplify very much the computations in order to verify that a map is a finite. So n in particular, when n is equal to 1 and p is equal to 2, that is, when we have a parametrized plane curve, delta associated to the parametrized curve is a very well known invariant that can be computed in terms of classical invariant in the theory of curves, in terms of the semigroup associated to the curve. If you have a plane curve, you collect orders of all elements that we can. G is a power series in X and Y, or G is an element of the local ring O2 composed with the parametrization. We have a series in T, you collect this order, the order of this series. So gamma is a subset of the natural numbers union with 0, and delta have a lot of properties. One of them, some of them, is that the semigroup is finitely generated with respect to addition. The complement and the complement of gamma in N is the set of gaps of the semigroup, and delta of the parametrization, delta of the parametrized curve, is exactly the number of gaps of the semigroup. That we can compute the delta invariance in algebraically. So, and all these objects was important for to prove this result that in 2019 we classify all monomial parametrized surface from in C4 using all these elements, the semigroup associated to this curve, the delta of the curve, and in order to compute the delta of this map. So this theorem says that F is a finite, F monomial is a finite if and only if is A equivalent to an immersion or has a parametrization given by X, Yn, Ym, X lambda Y. So our purpose now in this new work is how to produce new classes of a finite map-germs. For instance, if you start with a parametrized curve, not necessarily a plane curve, a parametrized curve in CK. Suppose that this map Pk is afinite. And the question is, we start with a map that has a parametrized curve as a component of the map. For which component we choose here in order to obtain that this map is afinite? In the first moment, it's a very general question, but we put some informations in order to try to obtain an answer for this question. We fixed the source dimension, F from CN to CP, N is fixed, P in the first moment is free, F is current run, and A finite, with this condition over P. And if F is current one, it's very well known that there is change of coordinates, that you can assume that n minus 1 first components of F is x1, xn minus 1. If you impose that we have a curve, parametrized curve as component of F, the question is which components we choose here in order to obtain that F is afinite. We give one possibility. For example, if we choose that P is 2n plus k minus 2, k is the embedded dimension of the parametrized curve, this map-germ that has a curve as a component, if you choose this possibility to the other components of F, this map is afinite. But it's not only one example of a class that answer this question. If we consider the same map F and change the curve. Not we consider in this proposition, we don't assume that the parametrized curve is monomial. But here, for simplicity, in order to simplify the notations, we consider monomial. We consider a plane curve, or a curve in C3, or a curve in CK. And here, all these maps are afinite, and we choose any coordinates here that not change the first principal part. There are a lot of examples of afinite maps. With these maps, we can construct a lot of, including non-monomial map terms, that is afinite. And we can put this question in a more general context to this following way. Given two map terms, f and g, not necessarily a curve, is there a map H such that this new map is afinite, where F appears as a component, G is another component of this map, and we want to know who is this map H in order to have that new map is afinite. All these questions was a motivation to define this operation that we call a join operation. We start with two maps, F and G. F is from Cn to Cp1, G is from Cn to Cp2, and which means to join F and G. Join F and G with respect to the map 8 is a new map term that in some sense preserve the properties of F and G. In some sense, we have map F appear here, we have a map G, and 8 mix the two variables. I'm not put any conditions. Here's a general definition. Of course, we can extend this definition for a finite number of maps. If you consider the join of R maps, the definition is consider F1, Fr, and 8 is a map that join F1 and Fr. This is the name. The name means this. We have two maps F and G, and 8 join the both maps in this sense. And this definition of join operation behave well with respect to A equivalence in the sense that if F is A equivalent to F tilde and G is A equivalent to D tilde, the join on F and G with respect to 8 is A equivalent to F tilde join with G tilde with respect to a new map germ A tilde that's A equivalent to 8. Well, in particular, we try to construct a map that we have in the first moment co-rank 1 and a parametrized curve. You want to discover which map 8 is necessary to consider in order to have a finite map. So this map that we presented before is a join of the identity with a parametrized curve. For which map 8? For this map 8. Yeah. And what else? What else? All these definitions, join operation, is not only to construct one possible class of map that's a finite. No, it's a pure in fact. In this theorem, we prove this theorem generalizes the classification of monomial map germs from C2 to C4. In first moment, we believe how many possible afinite map germs you can have if the map is from Cn to C2n, monomial and afinite. Perhaps in first moment, we believe that there are a lot of classes, but no, in fact, we don't have. If F is afinite, F is A equivalent to an immersion or is given to this way. We have one parametrized curve, plane curve, and this map is given to this way. That is, all monomial map germ find determined is a map. If not an immersion, is a co-rank 1 map, and the properties of this curve are essentially to characterize this theorem. And which more classes we can characterize? It depends on the hypothesis that you consider. For instance, if we fix the curve, we fix the parametrized curve. We fix the curve and we consider F, for example, we fix the target dimension. F is from Cn to C2n plus k minus 2. If F is monomial and has this curve as a component, that is F0i is 0 and we have a parametrized curve here, F is afinite if and only if is A equivalent to the join of the identity with a parametrized curve that is A equivalent to this class. So we can characterize other classes, but it depends what hypothesis do you want to analyze. Well, and why we decide to study map germs with a curve as a component? Not appear, it's not only one, we decide to study this. In fact, in this lemma, we prove that if F is from Cn to Cp, with P is greater than or equal to 2n, if F is singular, an afinite monomial map germ, there exists at least one afinite parametrized monomial curve as a component of the map F. These, I have some ideas of this proof, but essentially, this proof is reused several times in the next results. This is true because if f is affinite, by Gaffney's result, f is L-finite, this implies that the delta invariant is finite, so there is a power of the maximum ideal of On that is contained to f star OP, but f is singular, which means n monomial. It means that there exists at least one component of f that is given to this way, y m1, with m1 is greater than or equal to 2, because f is singular. But if delta is finite, it means that all elements in this power, the power of this maximal ideal, can be obtained by the components of the map. But if you have one component that y m1, in order to this invariant is finite, we need to have a curve in this variable, a parametrized curve that is finite, afinite. So with this lemma, I think this justifies why to study maps with this product. But okay, but until now, we studied the join maps in which we join identity with one parametrized curve. And if we join two curves, that is, if you have two parametrized curves, and the question is for its map H, the join of these two curves is afinite. We have some examples. For example, the map G from C2 to C6, given by x3, x4, y5, y6, x2, y, x, y3, is an afinite map, correct to all the other results. These maps, those maps are correct one. This example shows a map that's correct too, and is afinite because the delta is 48. So we have two curves. Notice that we have two curves, two parametrized curves, and we choose the map H as x2y, x, y3. So this is the join. This map is a join of these two curves. And it's possible to prove that if we consider generic curves, xn, xm, yr, ys, with this general x lambda 1, y, x, y lambda 2, this map is afinite. We choose one variable, we fix the variable x, a power of x product with y of degree 1, and x of degree 1 with the power of x. We can choose any lambda greater than or equal to 1. So the generic answer to this, if we join two parametrized curves, we can join a finite number of curves. And if we consider n parametrized curves, we join off them. For instance, we prove that if we choose a convenient map 8, this map is afinite for each weight. Each curve is afinite. Each parametrized curve is afinite, and choose a map 8 as a generalization of the previous result. We look at the variables of this map is y1, yn. So we fixed y1 with a power with all the other variables of degree 1, and you consider the last variable with a power with all the other variables of degree 1. We prove that this map is an affinite current and map germ. Well, but and now, And we have a lot of classes, of course. We can describe a lot of classes of maps. These parameterized curves are not necessarily monomial. And on this information, the join of the identity with one parameterized curve or join parameterized curves describe all monomial affinite map germs from Cn to Cp with p is greater than 2n. For me, phi chi j denotes a parameterized curve. X bar denotes the variable x1, xn minus q, and y denotes the variable y1, yq. With this theorem, we can construct a lot of classes of maps of any rank. Of course, for p greater than 2n. So let's start the hypothesis of this result. Let F from Cn to Cp be a singular current Q monomial map germ. We start with F monomial of current Q. If F is current Q, you know that the first components we can consider change of coordinates that the n minus k variables is x1, xn minus q that appear here, the identity in Cn minus q. This first component is because the map is current Q. Okay. In all other variables, we have any variables, the other variables y1, yq, by the previous lemma, we need to have a curve in each variable. We need to have a curve in the variable y1, we need to have a parameterized curve in the variable yq. Okay, what else? This map until here is not infinite. We need, because the variables are independent, the variables x1, xn minus q, here only appear the variable y1, here appear the variable yq. We need to mix all variables. And this is what which appear in the map 8. In the map 8, we have all products of power of a variable xy with the variables yj of degree 1 here. These notations means this. X bar lambda I1 yj means this. A power of the first variable with the other with yj of degree 1. And here we mix the variables y1, choose a power of y1 with the others of degree 1, etc. And is the general form, because here, until this point, 8 can be 0. This map is infinite. We put all what is essentially to guarantee that this map is infinite. But we can choose what I want for the map 8, that this map is infinite. It's not necessarily we need to consider all these products. It's possible to eliminate. For example, if all powers is equal to 1, we can reduce this element. Now we give some examples to finish my talk in order to construct, to show that it's possible to construct a lot of classes of affinite map germs. Fixed F from C2 to Cp, and we impose that F is affinite, a singular monomial map. And current one, we start with a current one map. For the previous theorem, current one map with this hypothesis from C2 to Cp is given to this way. X, a parameterized curve, we denote the variables of this map, X and Y. X, we have a parameterized curve in the variable Y. It needs to appear X lambda Y. and 8 we choose the general. When P, for example, if P is equal to 4, we have only this class. The singular monomial is given because we classify all parametrized surfaces, monomial parametrized surfaces with the property that's A finite. F is A equivalent to this class. If P is equal to 5, we can have other possibilities. For example, here we choose a current one, we have this component is X, we choose a curve in C3 and X lambda Y. Or we can choose a plane curve, X lambda Y, and 8 is free. Any monomial, of course, monomial that not change that we have before. We choose, including we can choose 8 is equal to 0. Here we decide to fix P equal to 7. We choose a curve in C4. This element we consider X7Y, and without this element, this map, if you choose 8 is equal to 0, this map is a finite, but we decide to put this element X3, Y5. Okay, here we have a lot of classes of current one monomial maps from C2 to CP. If for current 2, by the previous theorem, we need to have a parametrized curve in the variable X, a parametrized curve in the variable Y, and the others given to this way. If P is equal to 5, F is equivalent to this class. And here we have other possibilities that you can construct other classes of current 2 map-germs from C2 to CP. I think I don't have more time. Thanks for your attention.